Okay, so this problem says the angular velocity of a rotating rigid body increases from 500 to 1500 revolutions per minute in 120 seconds. Okay, so this is in minutes, that's in seconds. So either convert that to minutes or that to seconds. Okay. What is the angular acceleration of the body? So we'll convert 120 seconds to 2 minutes. Okay. So omega final equal to omega initial plus alpha times t. Alpha is okay, that's 1,000 divided by 2, 500 revolutions per minute squared. Okay. And if you wanted to convert this to radians, each revolution has 2 pi radians, and 1 minute is 60 seconds. So minute square would be 3,600 seconds. So 3.14 divided by 3,600 times, times 500. So this works out to 0.87 radians per second squared. All right. And this says, through what angle does it rotate, turn in 2 minutes? So theta minus theta initial is omega initial times time. All right, so the angular displacement will do it in revolutions. So omega initial is 500 revolutions per minute. T was 2 minutes plus 1/2. Alpha was 500 revolutions per minute square times 2 minutes square. So the angular displacement in revolutions is, this is 1,000 revolutions, and this is another 1,000, so 2,000 revolutions. And if you want to calculate this in radians, 1 revolution is 2 pi radians, so it's 4,000 pi radians. Okay. And if you wanted to find it in degrees, 2,000 times 360 degrees. Yep. 1 revolution is 360 degrees. This says a flywheel slows from 600 to 400 revolutions per minute while rotating through 40 revolutions. What is the angular acceleration of the flywheel? Okay, so we'll use this formula for this. Omega final square is omega initial square plus 2 alpha theta minus theta final minus theta initial. Okay, so we'll use revolutions per minute. Okay, and so this is also in revolutions. So this is 400 square equal to 600 square plus, actually let me do this. Alpha is omega final square minus omega initial square, 2 theta final minus theta initial. 400 square minus 600 square, and this was revolution square over minute square. Revolution per minute was the unit for this, and when you square it, that's that. And then 2 times 40 revolutions. So the units would be revolutions per minute square. And so this works out to so alpha is that. What does the negative sign indicate? It's slowing down. Okay. And then part B says how much time is elapsed during the 40 revolutions. Okay. So you want a formula that involves time, and here is a formula that involves time. Okay. So we know the final angular velocity, we know the initial angular velocity, and so on. So T is omega final minus omega initial divided by alpha. Okay. 400 minus 600 divided by minus 2,500. This was revolutions per minute divided by revolutions per minute squared. So what you'll get is a minute on the top. Okay. And so minus 200 over 2,500. So works out to 5 seconds. Okay. So this problem says a rod of length 20 centimeters has 2 beads attached to its ends. Okay, so the rod with beads starts rotating from rest. If the beads have to have a tangential speed of 20 meters per second in 7 seconds, what is the angular acceleration of the rod? Okay, so let's say it's rotating about that point, and here's the linear speed equal to 20 meters per second after 7 seconds. Okay. Okay, so this is 10 centimeters. Okay. And the linear speed is related to the angular speed is r omega. Okay, so you want this speed to be 20 meters per second after 7 seconds. So we can calculate what is the angular speed at that instance. Okay. So the angular speed is v over r, which is 20 meters per second divided by 0.1 meter. 200 radians per second. See, it's dimensionless, so that will be radians per second. So you want a final angular speed of 200 radians per second after 7 seconds. So now we go to this formula, and so the angular acceleration would be omega final minus omega initial divided by t. Omega final is 200 radians per second minus 0. Initial speed was, angular speed was 0 radians per second, and all this happened in 7. Okay, so radians per second squared. So 28.6 radians per second squared. So this problem says a man stands on a merry-go-round that is rotating at 2.5 radians per second. If the coefficient of static friction between the man's shoe and the merry-go-round is 0.5, how far from the axis of rotation can he stand without sliding? Okay, so I'll do a top view, and so there's a merry-go-round rotating, and there's the man standing. Okay, so what is the man doing as the merry-go-round is rotating? Oops. Okay. So the man is going in a circle. To make an object go in a circle, you need a centripetal force, or he's having centripetal acceleration. And V is R omega. So R square omega divided by R, which is R omega squared. Okay, omega is constant. So the further out you are, the greater your centripetal acceleration. Right? What is providing the centripetal acceleration? What is providing the centripetal force? Static friction force. Okay? So the static friction force. And what do you know about the static friction force? It can vary, and it has a maximum value. Okay? And the maximum static friction force is mu s times the normal force, and the normal force on him is, so this is the top view, he's standing on this merry-go-round, the normal force is equal to his weight, mu times mg. And so this gives you the maximum distance he can stand. Okay? If he stands beyond that, he'll just be flung away. Okay? His shoes can't hold him down. Okay? So R max is mu s. Oh, this is, and times. So this was centripetal acceleration. Centripetal force is m times r omega squared. So times m. So mu R max is mu s mg divided by m omega squared. The mass cancels, so everybody wearing the same shoes will be flung off beyond that point. Okay? So that's what that means. So R max is mu s times g over omega squared. And let's see if this makes sense. The stickier your shoes, the further you should be able to stand. Yeah. The faster you're spinning, the closer you need to stand. If the angular velocity is infinite, you need to stand right on the axis, not to be flung up. Okay. All right, so this shows you a system of point particles is shown in the following figure. Each particle has mass 0.3 kgs, and they all lie in the same plane. So this is the plane they lie in. What is the moment of inertia of the system about the axis given? So here's the axis, and this axis is perpendicular to the plane. Okay, so it's coming out of the paper. If the system rotates at 5 revolutions per second, what is the rotational kinetic energy? Okay, so the moment of inertia is, what are the moment of inertia of the system? MI/RI squared. And since the mass is the same, it's MRI squared. Okay. So the mass is 0.3 kgs, and this distance is 0.4 meters, so 0.4 meters square plus 0.2 meters square plus 0.6 square meters square. Okay. So the moment of inertia is, this is 0.16, 0.04, so 0.2, 0.56. So 0.3 times 0.56. And that is 1.5, 1.68 kg. Oh no, 0.168 kgs. Okay. So the moment of inertia of this object is 0.16 kg. And in part B, you're finding what is its kinetic energy. Kinetic energy is 1/2 I omega squared. In this formula, what are the units for omega? It has to be in radians per second squared. Radians per second. So omega is 5 revolutions per second, which is 1 revolution is 2 pi radians, so 10 pi radians per second. All right, so this works out too. And what are the units for kinetic energy? I'm sorry? Joules. Mm-hmm.
When you did the inertia, why did you, how'd you like 0.4, 0.2, 0.6 for all the radius?
That's in meters, 0.4 meters.
Oh, you needed meters, oh, okay, I see.
They're meters squared. So this problem says a system consists of a disk of mass 2 kg. So there's the disk, and radius 50 centimeters. So the disk is about this big. Upon which is mounted an annular cylinder of mass 1 kg. So this is the cylinder with inner radius 20 centimeter and outer radius 30 centimeters. The system rotates about an axis through the center of the disk and the annular at 10 revolutions per second. What is the moment of inertia of the system? So the moment of inertia of the system is the moment of inertia of this plus the moment of inertia of that. It's just like the mass of several systems is just the sum of the masses. So the moment of inertia is about any given axis is that. Okay. So the total moment of inertia is the moment of inertia of the disk plus the moment of inertia of the ring. Okay. The moment of inertia of the disk is mass of the disk. And for a ring, you can look it up, is 1/2 mass of the ring times inner radius square plus outer radius square. Okay. See, if the inner radius goes to 0, then the formula for the ring will become that for the disk. Okay. Here, anyway, you can look up that formula on the table. Okay, so let me. See, there's the formula for the ring. 1/2 inner radius, outer radius square. Okay. All right, so let's put in the numbers and calculate this. So mass of the disk is 2 kgs, and the radius is 0.5 meters square plus 1/2, 1 kg, and 0.2 square plus 0.3 square. And this is kg meter square. So this is 0.25 plus, this is 0.04 plus 0.09, 0.13 times 0.5, 0.065, 0.315 kg meter square. Okay, so that is the moment of inertia of the combined object. And then kinetic energy is, kinetic energy is 1/2 I omega square. Omega is 10 revolutions per second. Each revolution is 2 pi radians, so 20 pi radians per second. Okay? And you can substitute that in there. So there's I and there's omega. Okay, so there are several forces acting here on this system, and there's the axis of rotation coming out of the plane. All these forces are in a plane. Okay, so the axis is perpendicular to this plane. Calculate the torque about the z-axis. So here's the x-axis, y-axis, and the z-axis is coming out of the plane. How do you figure out the direction of the z-axis? Again, you use the right-hand rule. Turn from x to y, and the direction in which the screw moves is the z-axis. Okay, so if you turn a screw from x to y, it'll come out of the plane of the paper, and that's the direction of the z-axis. So you're applying these forces. Okay, this is 90 degrees. Torque is R cross F. Okay, and the convention is taken as if a force rotates an object counterclockwise, that's positive torque. So R is over there cross F. It would be R cross F would be along the z-axis. And if a torque is rotating the object clockwise, it's taken to be negative. R cross F, that would rotate the object clockwise. That would give you a negative torque, and the torque is pointing in the negative z-axis. Okay, so the torque is pointing either in the positive z-axis or negative z-axis. So if a force is rotating the object counterclockwise, that's taken to be positive torque. All right, so again, the magnitude of the torque is the magnitude of the force times the perpendicular distance or the moment arm. Okay. So this is a clockwise torque. So the net torque is the torque due to 1 plus the torque due to force 2 plus the torque due to force 3 plus the torque due to force 4. Okay, we can add them because all the torques are along the z-axis. So either along the positive z-axis or along the negative z-axis. So you're just adding a bunch of scalars. Okay. This guy is a negative torque. So this is equal to F1 is 3 newtons minus 3 times 3. Torque 2 is positive. Now here's the deal. This force can be broken up into this component and that component. This component is passing through the origin, so we'll have no torque. So it's just F2 cosine 30 times 2 meters. And that's positive. So F2 cosine 30 times 2 meters times 2. What is the torque for F3? Zero. Why is it 0? The moment arm is 0. It's passing through the axes. Okay? So the torque due to F3 is 0. And the torque due to F4, there's the force F4. You can break that into this component and that component. This component is passing through the axis, will have 0 torque. So it's F4 cosine 20 times 2 meters. And this is a clockwise torque. So this is a clockwise torque. So it'll be negative. Okay. Times 2. And what are the units for torque? What are the units for torque? Newton meters. Okay. Now Newton meters, in the previous chapter we called it a joule. Okay. So but when you're referring to torque, we'll keep it as Newton meters to distinguish it from energy units, even though the units are the same. So we'll always say Newton meter. And if you look up your numbers for your cars, it'll probably give in foot pounds. Okay, pounds being the units for British unit for force, and foot being the unit for. All right, so let's do this. So the net torque is minus 9 plus F2 is 2, so 4 cosine 30. 4 cosine 30 is 3.46 minus F4 is 1.8, so 1.8 times 2, 3.6 times cosine 20. So the net torque is negative 8.92 Newton meter. So if all those forces acted on this object, so imagine a disk there, and all these forces acted on this, and if the disk was at rest, which way would it start rotating? Clockwise. Yep. Very good. So this says a seesaw has length 10 meters. So this is 10 meters and a uniform mass of 10 kg. And it's resting at an angle of 30 degrees with respect to the ground. The pivot is located 6 meters at 6 meters. So this is 6 meters and this is 4 meters. What is the magnitude of the force needed to be applied perpendicular to the seesaw at the raised end so to allow the seesaw to barely start to rotate? Okay, so you're going to apply force like that. This is 4 meters. And where is the center of gravity? The center of gravity is there, and that's where the weight of the seesaw is acting. Okay, so this guy is rotating him clockwise, and this guy is trying to rotate him counterclockwise, and they're balanced. Okay, so you're calculating the torques about this point. Okay, this angle is 30 degrees. Okay, so we're calculating the torques about this point. So this angle is 30 degrees. I guess I'll need a bigger diagram, 30 degrees. So the moment arm is, this guy is 1 meter. 1 cosine 30 is the moment arm for this force. Okay. So you want the net torque to be 0, okay, because it's not accelerating yet, it's going to move. This guy has a counterclockwise torque which is positive, so F times, what is the moment arm for that? 4 meters minus mg times 1 cosine 30, and you want that to be 0. So F equal to mg cosine 30 divided by 4. Okay. And m was 10 kgs. Well, actually, I'll calculate it in terms of. So you see the weight is acting there, and you're applying a force. The weight is acting at 1 meter, but the moment arm is less than 1 meter, and you're applying a force perpendicular. You have a moment arm of 4 meters. So the further out you are, the smaller the force you're applying. The force you're applying is 22% the weight of the object, of the board. Okay? Mm-hmm.
How did you ever multiply the mg times the 1 times cosine 30? Like, what did you do that?
Okay, let me do a bigger diagram. So there was the pivot point. And here is mg. The moment arm for mg is this distance. And this was 1 meter. This angle was 30 degrees. That angle is 30 degrees. So this is 1 cosine 30.
How did you get the 1 meter?
this distance was 6 meters. The center of gravity is at the center, which this makes it 5 meters. So that's 1 meter. Okay, so we'll do this one last problem. A clay cylinder of radius 20 centimeters on a potter's wheel spins at a constant rate of 10 revolutions per second. Okay, so the potter applies a force of 10 newtons to the clay with his hands, where the coefficient of friction is 0.1 between his hands and the clay. What is the power that the potter has to deliver to the wheel to keep it rotating at this constant rate? Okay, so here's a top view of the potter's wheel. The guy is pressing with the force of 10 newtons. Okay, and if the wheel is rotating in this direction, the friction force will be like that, and it's a kinetic friction force because the wheel is moving. Okay, and all right, so the friction force is mu k times the normal force, and the normal force is F. Okay, so it's 0.1 times 10 newtons equal to 1 newton. That's the friction force. Okay. Now, to keep it moving at constant velocity, you have to apply a force that's equal to the friction force. So the applied force needs to be equal to the friction force. Okay, that is, what is applying that force? The motor is applying that force. Okay, and so sort of you can think of the motor, and it's rotating at 10 revolutions per minute. So, and the radius is, okay, the radius is 20 centimeters. So power is torque times omega, and torque is applied force times R, and omega is 10 revolutions per second. So 20 pi radians per second. So 1 newton times 0.2 meters Okay, so that's the power of the potter's wheel. Power is in watts, so 12 watts. All right, guys, so we'll stop here.